Okay, welcome to Physics 2010. To start off with, I want to let you know that the software I'm using to record these videos limits me to 15 minutes. So I'll be recording as long as I can. If I see a good stopping point before my 15 minutes is up, I'll stop. Hopefully I won't get cut off. So you'll be seeing several videos per chapter, and I've got a lot of other resources on Blackboard as well, so check them out also. So in this first chapter, we first talk generally about what science and physics is, and then we deal a little bit with measurement and significant figures and units. So science is basically a way of explaining why things happen. So it starts by making observations. We see the world around us, and we begin to wonder why certain things behave the way they do, and we come up with theories to explain these observations. But then we need to go on to test our theories to see if they are really true and if they will be true in a variety of different circumstances. So the observations will lead to tests, and tests lead to data, and then we organize that data in some way. We analyze it, we compare it to our theories to determine if they were correct or not. Here's a quote from Adam Savage that I like. The only difference between screwing around and science is writing it down. So this really emphasizes the importance of recording data in order to analyze it. Science can be fun. I think it is fun. But it's important to gather data in order to test the theories. And that basically is the scientific method. Here's a graphic organizer that shows the scientific method of having observations, which leads us to question things like why something behaves in the way it does. We come up with a hypothesis, and basically a hypothesis is a guess as to why things occur the way they do. And then we perform some type of experiment. We do something and observe the results of it. We collect and analyze data, and then that leads us to a conclusion. Okay, and then the conclusion might lead us to additional observations, and this is really a cycle that goes on and on and on. Science is constantly refining its laws or theories and always striving to gain a deeper understanding. And so these hypotheses, once they have been tested, can lead to theories. And if the tests in a variety of different circumstances all support the original theory, then they become generally accepted by the scientific community. And they can go on to explain greater and greater ranges of phenomena. So physics, you may be thinking, why do I need to know physics? Many of you might be in an engineering technology program at Zane State College, but even if you are not in an engineering technology program, physics relates to a wide variety of fields. These are just some of the fields listed by the textbook, but honestly, it's a pretty short list. The actual list is much greater. The textbook does tend to specifically, and I believe intentionally, use a lot of examples that apply to the medical field and how physics is in our own bodies, whether it's the electrical impulses in the nervous system or the fluid dynamics of blood going through our veins, or the stress-strain relationships of our bones. Physics is literally everywhere. So I've already touched on some of these terms already. A model is a way to help you visualize something. Models are not always literal. They're sometimes figurative, and they're basically just a way to help visualize something that might otherwise be difficult to visualize or think about. And so, as I said before, a hypothesis can lead to a theory if it has been tested over and over again and the test results support it. Then you can develop a theory, and eventually that theory may become a law. We have down here a little clip art image of Isaac Newton and the apple falling. It's probably one of the better known stories of a scientific law being developed, the law of gravity. So the difference between a principle and a law is that a scientific law has been tested many times, and it is never not true, and it can be applied to a broad set of circumstances. So the law of gravity applies regardless of what planet you happen to be on, or if you're not on a planet at all. It applies to all different objects of different shapes and sizes and materials, so a very broad set of circumstances. A principle is similar to a law, but it isn't. It cannot be applied as to circumstances that are quite as broad. It applies to a narrower range of phenomena. So let's start talking about significant figures. Significant figures is something that will be a part of our homework assignments and tests and labs throughout the entire semester. This is not something we're just going to learn about and then forget. It's going to be emphasized throughout the entire semester. And so it's important to understand this so that it can become almost second nature to use. And it's important to understand why significant figures are important, not just to do it because the teacher says so, but to understand exactly why it is it's important. So when we perform a scientific experiment, we collect data, and that data is often some type of measurement. Now, depending on the tool being used to gather that data, you're going to have varying degrees of accuracy. In the image here, we're measuring a piece of lumber, a 2x4, with a metric ruler. So the smallest increment of measurement on here is a millimeter. We can't really measure the width of this 2x4 with a degree of accuracy greater than 1 millimeter because our instrument that we're using to gather the data is limited to that level of accuracy. So if we were to, say, measure the width and the height, and then we multiply those two numbers together to find an area, we really shouldn't be getting an answer for an area that has an accuracy greater than 1 square millimeter. So our accuracy is limited by the instruments we use, and if we then manipulate that data, whether we're multiplying, dividing, adding, or subtracting, we need to make sure that the answers we get from those mathematical operations do not end up giving us an answer that has an accuracy level greater than what the original data was measured with. So there are different ways we can express our accuracy. We can express it with plus or minus a certain amount of data. For instance, here, if we are measuring length and we measure something to 8.8 centimeters, then we might have a degree of accuracy of plus or minus 0.1. So this might be the width of that 2x4 we were measuring. We found it to be 8.8 centimeters, but it could be maybe 1 millimeter greater or less. 0.1 centimeters is 1 millimeter. So we can just express it with the amount that it can be above or below, or we can express it as a percentage. So if we take that 0.1 centimeters and divide it by the length, so this is the, we could call this the delta or the error, the tolerance amount, and this is the original measurement. So if we take that 0.1 out of 8.8, that's sort of like a fraction, and if we multiply it by 100%, we get a percentage here. So it would be plus or minus 1% would be our accuracy level for this measurement. So let's talk significant figures. So first of all, when you see a number, any number that is non-zero is significant. So here we have the number 145. We've got a 1, a 4, and a 5. None of those numbers are 0, therefore they are all significant. So this has 1, 2, 3 significant figures. Pretty straightforward. All zeros that are bounded by a non-zero digit are also significant. So for instance, here we have the number 2013. It has 0 in it. Okay, zeros can be significant or non-significant or insignificant. So which one is this? Well, it has a significant 2 on one side and a significant 1 on the other. Therefore, it is also significant. So we've got the 2, 0, the 1, and the 3. All 4 of those numbers are significant. Here's another example. We've got 2 zeros right here. Are they significant? Well, we've got a 3 there and an 8 there. Those zeros are in the middle. So we've got 1, 2, 3, 4, 5. 5 significant figures. Okay, our third significant figure rule regarding zeros is if they are trailing beyond the decimal point, then they are significant. So in this example, we have 4.000. Okay, and since they come after the decimal point, they are significant. 1, 2, 3 plus the 4 gives us 4 significant figures. Now, the way I like to think about this or remember it is this 4.000, if you were to write that out, 4.000, you didn't have to write these zeros. Okay, the person that wrote this number didn't have to write it. They could have left them off and just written 4. Okay, 4.000 and 4 is essentially the same value. So if somebody took the time to add the 0.000, and they didn't really have to, then they must have done it for a reason. Therefore, they are significant. Okay, the 320.00. Now, this 0 doesn't come after the decimal point. It's before. But since these zeros are after the decimal point, then they are significant. They were put there for a reason. And the 3 and the 2 are significant. And if we remember back to the rule that if you have a 0 that comes between or is bounded by significant figures, then it is also significant. So that one is too. So in this example, all 5 of those are significant. Okay, now if there is no decimal point or the trailing zeros come before the decimal point, then they are considered not significant. So 4,000, 4000. So could we leave off those zeros? 4,000. If I wanted to write this, if I just wrote 4, well, clearly that's a different value. 4,000 and 4 are two very different numbers. In order for this to be 4,000, you have to put these zeros in here. They are required as placeholders. So they're not significant. They have to go there as a placeholder. They weren't put there intentionally. So they are not significant. So zeros at the end of a number that come before the decimal point are not significant. So in this case, it's only the 4 that's significant. And in this case, it's only the 1 and the 2. All right, I've run out of time. We'll resume in the next